So I'm sorry I'm not Dr. Z. I'm Dr. Y. But I'm excited to be here anyway. Now I'm a solar astrophysicist. I study the sun, space weather. I am not an expert on Solar Orbiter. I know about Solar Orbiter, I know about Parker Solar Probe, and I'm happy to talk about anything. And also, if you guys, since this is a social, I do have a Twitter handle. The Sun Today is my Twitter handle. But why are we here? I mean, so you guys have talked to ULA folks to learn about the mission. Have you talked to any scientists yet?
Not yet.
No scientists yet. Okay, well, I'm a scientist.
It's our day.
You're our first scientist. Okay, so, well, why are we here? The sun. So we're here to talk about the sun's influence on the solar system. Okay, of course it's the center of our solar system, makes up 99% of it, provides us heat and light, the reason why we're here, the reason why we live, but it's also pretty dynamic and active and can be quite violent, and it produces a lot of interesting activity. Huge explosions called solar flares, sudden releases of light, enough energy to power the world for 100,000 years. Okay, they're massive explosions. But on top of that, the sun throws out billions of tons of solar material and magnetic fields. We call these coronal mass ejections. And both those solar flares and those coronal mass ejections happen because of the sun's magnetic field, the sun's magnetic energy. And when those explosions happen, they both often create massive shock waves. Okay? Kind of like we think of shock waves, you can think of sonic boom as an example. Okay? And those shock waves violently push the material on the sun, and they accelerate particles, fundamental particles, protons and electrons, the things that make up atoms, to speeds near the speed of light. Okay? And so those create these storms of high energy particles. Okay? And all three of those types of eruptions happen in conjunction with the sun's constant outflow, called the solar wind. Because it turns out the sun's atmosphere is a little bit odd. I mean, when you think about a heat source, you know, you're standing next to a campfire, you step away from it, it gets cooler. But that's not what happens on the sun. When you move away from the sun's atmosphere, the sun's visible surface called the photosphere, the part that actually is what we see, when of course you have the proper protective gear on, you don't want to look at it directly. But when you move away, that part of the sun's about 10,000 degrees, but as you move out higher up in the atmosphere, it gets hotter and hotter, okay, which is counterintuitive. You would think it would get cooler. It actually gets up to many millions of degrees. And this is in the outer part of the atmosphere called the corona. Now, hopefully, everyone remembered that in 2017 there was a total solar eclipse. Okay? And that is one of the unique times from Earth when you can see, if you're in the path of totality, the corona. This is that extended part of the atmosphere. And this is where all this activity comes from. This is where all this magnetic energy is released. But that atmosphere expands away and constantly flows away from the sun, called the solar wind. Okay? And so the solar wind and all of these eruptions, the solar flares, coronal mass ejections, and these particles create this crazy, complicated, dynamic environment through the whole solar system. And all this stuff coming from the sun interacts with everything. It interacts with the planets, their magnetic fields if they have them, their atmospheres, it interacts with comets, with asteroids. And so this whole study of this dynamic process between the sun and the solar system is heliophysics. Okay? And this environment, this dynamic environment, we typically call that space weather. Okay? So we have weather in space driven by the sun. And so that is one of the key things that we're trying to understand with missions like Solar Orbiter. We already had Parker Solar Probe launched last year, which is traveling very close to the sun, less than 4 million miles from the visible surface. But what Solar Orbiter is providing is a close-in view, not quite as close as Parker's Solar Probe, but the uniqueness is that it's actually moving out of the plane of the solar system. Okay? All the planets, including the Earth, orbit in roughly a plane. And one of the aspects of that is that means that from Earth, or even the spacecraft we normally have, gives us a view of the sun that's not complete. We don't see the poles of the sun very well. Okay? And that is a critical part of it because the magnetic field from the poles is part of the global magnetic field of the sun. And in order to understand that, we really have to understand what's happening at the poles. And so that is one of the key things that Solar Orbiter is providing to us. It's giving us this perspectives of the poles. We're going to be imaging them in several different wavelengths. We're also going to be studying the magnetic fields directly and the poles. And this is giving us all of the different pieces to this sort of complex puzzle of sun's activity and how it influences us. And it has a pretty big impact on us. We've become a very technologically dependent society. Our satellites are critical for the communication that we have, for the fact that we can have social networks that everyone is dependent upon. GPS is very much influenced by this type of activity from the sun, the stability of satellites themselves. And in the worst case, some of these solar storms can actually create electrical currents on the Earth that knock out power grids. But also, as we're traveling into space, as we're moving beyond low Earth orbit with the ISS, eventually going to the moon with the Artemis program, and then beyond, that environment that the spacecraft, and in particular the people that are on those spacecraft are encountering, is pretty hazardous. And so we want to be able to understand that environment, and maybe the ultimate goal is to predict that environment. You know, to predict space weather, much like what we do here on Earth. And that is something that requires us to really understand the fundamental physics of the sun. But actually, the other thing that I like to think about is understanding the sun not only tells us about our solar system, but it tells us about all the other solar systems that we've discovered. You know, we have found more than 4,000 extrasolar planets. We have launched recently the TESS mission, which is going to find tens of thousands of extrasolar planets. And in order to really understand those other star systems, we have to understand their interaction, those planets interacting with their stars. Because the whole idea of habitability is not just whether or not there's water on those planets, and in particular liquid water, but what's the environment created by those stars. Okay? And so as we understand what's happening on our sun, and even understanding what's happened in the past and what will happen in the future, we're taking that information and extending it to understanding these extrasolar systems, and whether or not they're capable of harboring life, and maybe even intelligent life. So that's kind of the big picture of what heliophysics is. You know, it's an interdisciplinary system science, and it's trying to really understand that complex interaction between a star and the planets around it. So that's Heliophysics 101. So
we'll indulge into advanced later. Huh?
What's that? Yeah, we'll go to advanced later. We can talk about plasma physics and particle acceleration and all that kind of stuff. It's a really cool field, and it has a lot of implications, and it's really important when we're studying heliophysics. Earth science is critical. Understanding the interaction between what's happening on the sun and what's happening on the Earth, how our atmosphere has stayed intact, tells us things like why Mars doesn't have an atmosphere. Okay, we think it did at one time have an atmosphere, but it lost its magnetic field, and that was critical for keeping its atmosphere. understanding planetary science really depends on heliophysics. So it's a pretty cool field. I mean, I'm a little biased as a heliophysicist, but I think it's a pretty neat field because it is so interdisciplinary and it connects with everything else that NASA does, and it's such a critical part of our ability to explore beyond the Earth. Questions?
Just keep talking.
Any surprises from the Parker probe?
We've actually had a lot of surprises from Parker. We recently, I think it was December, we had 4 papers that came out in Nature, which were some of the first discoveries from Parker. And there are a couple of things. One of the things that was surprising is as we moved closer to the sun, we actually noticed that the magnetic field coming away from the sun had these things that we've called switchbacks, where the magnetic field kind of did a 180 turn back on itself. This was something we didn't expect. We're starting to have a better understanding of the region around the sun that's dust-free. You know, the interplanetary space is full of dust. We can actually see that dust if you have the right conditions here on Earth. We call it zodiacal light, okay, the zodiacal dust. That dust is made up of comets, asteroids, and as you get closer to the sun's radiation, the sun's output ablates that stuff, okay, and it creates this region of dust-free around that. And that tells us a lot about the evolution of the solar system. This is information that we then apply to other solar systems, and so we have a better understanding of that from Parker. We have a lot better understanding of the kinds of turbulence, okay, as the solar wind is moving away from the sun. One of the things is, not only is it interesting that the sun's temperature increases as you move away from the surface, but the solar wind itself accelerates, okay? It actually speeds up. So there's a region just outside of the, well, just in the sort of lower part of the corona, where the solar wind all of a sudden kicks up and speeds up. We didn't really understand that region, and we're starting to finally see how turbulence works, how these structures, how dynamic they are, and how they evolve as we move away from the sun. So those are some of the things that Parker has discovered. Yes, sir?
With these studies, will this also give us maybe earlier warning signs for major solar flares that would affect our satellites or ISS? Or
That is certainly the hope, because one of the things in particular Parker will somewhat address, and hopefully Solar Orbiter will address even more, is the underlying mechanism that's generating the magnetic field in the sun is called a dynamo. Okay? The basic idea is similar to how magnetic field is generated inside the Earth, but we don't completely understand it. It's very complicated mathematics. We have computer models, but we don't, for example, know why is it 11 years. You know, the sun has an activity cycle going from low, high, back down to low, roughly 11 years. Sometimes it's a little shorter, sometimes a little longer, but we don't understand exactly why it's 11 years. Our computer models show there's a cycle, but we don't understand that particular aspect.
does the sun have its own leap year?
Well, it doesn't have its own leap year. That's something we made up. You know.
Well, yeah, I know.
But in order to understand that, we really need to better understand the physics. And so that's one of the hopes of Solar Orbiter, is to better understand that. So the long story to your answer is, if we're going to predict solar flares, we really have to understand the fundamental phenomenon that's happening inside the sun. Because we know these magnetic fields get twisted up. You know, you can imagine you have a rubber band, you twist it, it starts to knot up. And inside the sun, those magnetic fields become buoyant. They float to the surface, poke through the surface, and we have sunspots. Okay, that's where the magnetic fields are very concentrated and poke through. But what we don't know is, when are those sunspots going to erupt, or are they going to erupt? And right now, the best we can do to predict solar flares, for example, is we look at the sunspots, we look at how complicated they are, and we compare them to past sunspots. This is actually how we provide information about rain, rain forecast. It's going to 80% chance it's going to rain. And what does that mean? Well, that means that given the conditions on that day, we've looked in the past, and 8 out of 10 times, or 80 out of 100 times, it rained. Okay? That's not really a true prediction, okay? But it's a start, and
More
that's
of a guideline.
it's a guideline, yeah, and that's really the best we have with sunspots. We look at all the sunspots that have a certain complexity. We look in the past, and we say, 8 out of 10 times, a sunspot that looked like this, that had this magnetic field and this structure, erupted in a certain type of solar flare. But what we'd like to be able to do is to actually look at the structure and say, well, we know this is going to produce a flare in the next 2 days or 5 days or something like that.
Right.
So that we can have some warning. That's why we need to understand the physics, the fundamental physics. And that is the kind of goal that we're trying to reach with a mission like Solar Orbiter. And in addition, we have a recently new telescope called DKIST, the Daniel Inouye telescope in Hawaii. Now, that is not viewing all the same wavelengths we view from missions like SDO and Solar Orbiter, because it doesn't, we can't see certain wavelengths through the atmosphere. However, on the ground, we can make a really big telescope. Okay, so it's more than 4 meters in size. It's a large, large telescope. And that allows us to look at the structures on the sun that are causing the magnetic fields to become twisted in incredible detail. And also, it's allowing us to look at the magnetic field in the corona. Because when we talk about the magnetic field that we measure on the sun, we're actually measuring the magnetic field on the photosphere, where the sunspots are. But the problem is, the magnetic fields are releasing their energy in the corona. So there's a disconnect there. And all we can do is extrapolate from what we measure here to what's happening up here. One of the holy grails is to be able to measure the magnetic field in the corona. And now, with telescopes like DKIST telescope, we're actually able to make extremely difficult measurements, in particular in near infrared, to start to measure those magnetic fields in the corona, where it's much more complicated. But that's where all the interesting stuff is happening. Okay. So we're combining much more detail here on the ground with up-close observations at the sun with Parker, farther away with Solar Orbiter, but imagers looking on the poles to show us the magnetic field structure, to give us this complete picture of what's happening. And that's really, you have to fill in all these different areas to start to piece together this complex system. Yes, sir?
Can you talk about the magnetic flux when the coronal mass ejection? I'm sorry if I'm like
No, it's okay.
you wrong here, but when there's a coronal mass ejection, it has been observed that it twists.
Yes, so these magnetic structures on the sun, sunspots, and then something called a prominence, the magnetic fields are twisted. And when you have a twisted magnetic field, again, a good analogy is a rubber band. As you twist that, there's energy built up inside of it. Okay? And when these structures erupt from the sun, they have internal magnetic field. And there's twisting and structure and energy in them. So one of the things we want to understand is, as these structures are passing by the spacecraft, they can measure these magnetic fields directly. Because the structure of that magnetic field tells us a lot about how it will interact when it gets to the Earth. Because if you look at the magnetic field of the Earth, it roughly has a northward component in the front of the magnetic field, okay, what we call the magnetosphere. So if you take, I guess a good analogy, you take 2 bar magnets, okay, if you have them aligned the same way and you push them together, they repel each other. Okay, but if you take the bar magnets and you twist one so they're oppositely pointed, they attract, okay? So you imagine the same sort of thing happening. So I'm a coronal mass ejection, and I'm moving along, and I have an internal magnetic field. So the question is, what's the orientation of my primary component this way? Is it mostly oriented this way, or let's say this way, okay? Because if I'm traveling along and I get to the Earth, if my magnetic field is oriented roughly the same as the Earth, then energy is not transferred very easily, okay? You have sort of this repulsion. But if it's the other way, these magnetic fields connect, and energy much more easily flows into the magnetosphere. And that means it's going to jostle the magnetosphere, transferring energy into it, and we will much more strongly feel the effects of it. Yes, wrap it up. Okay, all right. Hey, thanks a lot. I appreciate it, especially me jumping in at the last minute. Thank you.
So, yeah, make sure you get a pic of the shoes.
We did.